Are we really out of bandwidth here? No, we're okay. Okay. So let's review those here in the notes. So if we have two groups on a central atom, that gives us linear geometry, 180-degree bond angles. If we have three groups, that gives us trigonal planar geometry, and that's 120 degrees bond angles. And four groups, the ones we just talked about, tetrahedral. Now remember that these geometries and these connections also go along with the type of hybridization on that atom. Hybridization comes from the mixing of the s and p orbitals so that we have an average overall orbital that we call a hybrid orbital. Again, there's some of that in the book that you can, in our book, that you can review in chapter 1, or you can go back to your Gen Chem book and review it there. But the nice thing about that is it all kind of goes along with this other stuff. So if you remember this, or if you can keep track of these three things, you can add the hybridization fairly easily. So you got sp hybridization goes with linear, sp2 goes with trigonal planar, and sp3 goes with tetrahedral. So let's look at some examples of some organic molecules and the things that we're going to be dealing with this semester that fit into these, because in Gen Chem you mostly, or in whatever class you took before this, you mostly dealt with inorganic molecules, like small things that just have one central atom and like 3 or 4 things around them. So let's look at what happens here with some slightly bigger molecules. So let's take a look at acetic acid. So first I'm going to draw a Lewis structure, like the way that we did it on the board. And then we're going to think about the geometries and the hybridizations and redraw it with that stuff in mind. All right, so here's our Lewis structure. Like that. Now in Gen Chem, you probably would have seen this written as a formula like HC2H3O2. Does that formula kind of look familiar? The C2H3O2 was the acetate ion, and then you add the hydrogen. In organic chemistry, that's a little bit confusing, because we can potentially draw a bunch of different molecules that fit that formula by rearranging our atoms. We're going to be less concerned with molecular formulas like that in this class because there's so many different ways you can connect these atoms. It's going to be a lot more helpful if we can use formulas that actually give us a hint as to how these things are connected. So when we write a formula for acetic acid, we might find it more useful to write something like CH3COOH, or sometimes CH3CO2H, which gives us a little bit more of a sense of how this thing is actually connected. It also tells us that COOH, that it is a particular type of molecule known as a carboxylic acid, which we'll talk about later. All right, so now, looking at acetic acid, looking at the molecule that I drew, I want you to talk in your groups about what the geometry should be at those 3 central atoms, what those bond angles look like, what the hybridization is, and then redraw it using the correct angles, and then we'll talk about it all together. Make sense? we got 3 internal atoms, C, C, and O. Talk about what their geometry and hybridization should look like. I now realize I forgot the electrons, so let me add those. But yes, yeah, that's good. Okay, did you get a chance to try this out? Maybe some ideas, think about it? Okay. So going back up to our thing here, remember that you can use this sort of for any atom, and those things always go together. So if we look at the leftmost carbon, how many things are attached to that carbon? How many electron groups there? 4. So that makes it tetrahedral with 110 degrees. Tetrahedral sp3, and that means the bond angles are going to be about 110 around that carbon. Okay? What about the next one? So that's going to be trigonal planar. What hybridization? sp2. And what bond angles? 120. Okay? And then this one is not linear. Why not? Anybody know why? Because you got to count the lone pairs too. So how many total things are around that oxygen? 4. Yeah. Yeah. So I'm actually going to put that in quotes because it is a little more complicated than that for this particular molecule. We're not going to get into why yet, but by next week you'll know. So same thing. So it turns out that oxygen, because of its proximity to that other double bond, actually can have more sp2-like character. But again, we're not going to get into that now. So let's just use what we know and try to redraw this in using that information that we just put down there. So the one on the left, we need to make into a tetrahedron, or a tetrahedral coordination bonded compound. So let's put an H here and an H here. Actually, no. Let's go the other way. It usually makes more sense to keep the backbone of the molecule on the straight bonds that are in the plane of the paper and make the things kind of hanging off like those extra hydrogens, the ones that are going forward and back. But it's not required. You can draw it however you want. Just makes it a little bit easier sometimes to see. So there's our CH3 with tetrahedral geometry. Our CH, or our C over here, has trigonal planar geometry. So that means we're going to take the three things connected to that carbon, this oxygen, and this oxygen, and we're going to put them in the corners of a triangle, so that there's 120-degree bond angles between each of those. And then the hydrogen we'll put on an angle kind of going off that way. If we want to then label these bond angles, that one should be about 110. This one should be about 120. And then the oxygen one, the next oxygen, gets a little weird, but for those two at least, we can be pretty certain of those. Okay, so this is generally how we're going to assign geometry and hybridization to our molecules in this class. We won't really see those kind of individual small molecules like you saw in Gen Chem. We'll be looking at bigger molecules like this and assigning geometries to the different atoms in the molecule. And if you take a look at the quiz, you'll see number 5 kind of basically is this. So we got a molecule with two kind of central atoms, and you have to draw it and approximate the different bond angles. Number 4 is kind of like that too. All right, any questions about that before we move on? Again, it's not like a huge problem if you don't remember this stuff very well from general chemistry, but this is the time right now to go back and refresh that and make sure that you do that before next week when we really start getting into new stuff. All right. Let's talk about polarity. So remember or recall that in general, a perfectly covalent bond, like one between two hydrogens, is evenly shared among both hydrogens. We would say that the electrons in that bond are in both pretty much equally. But if that were to be a different compound, like say HCl, we have a different thing going on. And so can anybody describe what's different about HCl in terms of where the electrons are going to be? Anybody remember? What? Yeah, more towards the chlorine. Yep, exactly. So the electrons are pulled more toward the chlorine. Anybody know why? What's the property there that causes that? It is bigger, but that's not necessarily what pulls the electrons toward it.
Higher electron.
Yeah, so I was going to say, yeah, property is called electronegativity. Electronegativity is the ability of an atom to attract the electrons toward it in a covalent bond. And we can look in the book for a chart of electronegativities. Grab one here. Let's see, which page am I going to? I'll put this in the notes so you've got it. Oh, that's too small. Let's try again. There we go. So any chemistry textbook is going to have a similar chart. Now we're a little too big. Of electronegativity values. Do you remember seeing something like this before? What's the highest electronegativity element? Fluorine. So you see fluorine up in the corner here with electronegativity of 4.0, and then things kind of go down from there. The trend is that electronegativities increase as you go toward fluorine. Now, for our purposes in organic chemistry, we can really ignore most of these electronegativities because we're just not going to encounter them much. So let me highlight for you the ones that will be important. Hydrogen. We're going to see a lot of hydrogen. And then kind of, let's say like just this little corner here. That's where we're going to be talking about most of our polarity, is that little red and orange corner. We'll occasionally see some phosphorus or something sometime, but we're not going to worry about it too much. So we've got fluorine is the most electronegative, and so in our HCl bond, we would say H has electronegativity of 2.1, Cl 3.0, and therefore there's a pretty big difference in electronegativity, and we would expect the electrons to be pulled toward the chlorine. And then the net effect of that is that we have a partial negative charge on chlorine and a partial positive charge on hydrogen, so that becomes what we call a polar molecule. That means that it has a negative side and a positive side. So when you're judging these things, like on the quiz, which says, like on number 5, you're drawing this molecule, and question E is this molecule polar? So you have to do a couple things to answer that question. One is you have to judge the individual bonds. So let's go back up to our example with, actually I'm just going to redraw it so we have the table here. Acetic acid. Okay, and we want to know what's the polarity of this molecule. Do we consider this molecule polar or nonpolar? And to do that, for a small molecule in general chemistry, you probably learn to add up the bond vectors or something like that and figure out if there's this overall difference. Organic chemistry, it's a little bit different because the molecules are bigger. So we kind of look at the individual bonds of the molecule, we find where the polarity is, and then we kind of decide if it's more based on one side or if it's kind of not there. So that doesn't make a whole lot of sense. But we'll do this and then we'll do another example and hopefully it'll make sense. So looking at that molecule, where do you see differences in electronegativity within those bonds? What? In the double bond, so we see a difference between, yes, we see carbon and oxygen having an electronegativity difference of about 1. Everything above 0.4 is considered polar. So if it's a difference of 1, that's a substantial source of polarity. So we would say, yes, both of those carbon-oxygen bonds are polar. So we can say that we would expect to see that this carbon is partially positive, this one's partially negative, and this one's partially negative as well because there's that difference there also. The fact that one is a double bond and one's a single bond actually doesn't really affect the polarity here, at least just looking at the electronegativities. So what else? Where else do you see a difference in electronegativity between two bonded atoms? The OH, yep, for sure the OH. So I know I cut off hydrogen, but hydrogen's 2.1, oxygen is 3.5, so that's a very large difference in electronegativity there. So we would expect, again, to see a polarity difference there. And what about the carbon hydrogens over on the left? Do we see a big polarity difference, or do we see a polarity in a carbon hydrogen bond? We don't. The difference in electronegativity between carbon and hydrogen is small enough that that's considered nonpolar. So carbon-hydrogen bonds are nonpolar. Carbon-carbon bonds are nonpolar because it's the same thing on both sides. So our polarity comes from the carbon-oxygen and oxygen-hydrogen bonds in this molecule. So